Hello students and welcome to Lesson 1 of Unit 5 Part 2. In this lesson we will be creating input-output tables to represent relationships. Our essential questions are 1. Given a partially completed input-output table, how can I find the rule and complete the table? And 2. Given an equation, which is a rule, how can I create the input-output table? So let's review. Relations represent relationships, and they exist all around us. As a relationship occurs between two or more things, it may create a consistent, reliable, predictable relationship. This type of relationship is called a function. Since a relationship is between two or more things, there will be two variables, an independent variable and a dependent variable, in the relationship. These relationships can be represented 5 different ways: in context, in words, as an input-output table, as a graph, and as an equation. Today we're going to look at an input-output table, which we know is one way to organize a few different contexts using columns and rows. So our first skill that we want to be able to do is to extend input-output tables. So if we're given a partially completed input-output table without a specific rule, look for a constant rate of change to decide how the values function. So for example, here is an input-output chart. So these are our x values, these are our y values. And we see that the input is increasing by 1 every time, which creates consistency. We see that the output is decreasing by 4 and decreasing by 4. You could also say that 8 was divided by 2 to get 4, but that doesn't work here. 4 divided by 2 is not 0. So that relationship only holds true for one set of the variables, not all of them. Do you see how consistently it's subtract 4 for each term? So if we see that relationship and we see that the outputs are decreasing by 4, that's our constant rate of change. So 0 minus 4 is negative 4, and negative 4 minus 4 is negative 8. We can extend this input-output table even further if we continue to increase the input by 1, so it'd be 6, and decrease the output by 4, which would be negative 12. And you could continue extending your table as far as necessary. So let's look at 2 more examples like this. We'll look for a pattern and then we'll extend it. So look at our inputs. We have it's increasing by 1, increasing by 1, increasing by 1, and this creates consistency so we can look for a pattern to see if this functions. Now look at the outputs. We're at negative 12, it goes up to negative 6, which would be add 6. And negative 6 to 0 is also add 6. So we see that consistent pattern, and we can extend it further by adding 6 again and adding 6 again to complete the partial table. Now, sometimes there is not a consistent relationship between the outputs. Do you see how the inputs are increasing by 1? But the outputs vary in the way that they are increasing. Here we increase by 3, here we increase by 5. If this happens, there is still a pattern in the way they increase. But if that happens, look at the way these inputs and outputs are related. What can you do to 1 to get 1? That you can do to 2 to get 2, that you can do to 3 to get 9. Well, we know that 1 times 1 is 1, so if we square 1, we'll get 1. 2 times 2 is 4, so 2 squared is 4. 3 times 3 is 9, so 3 squared is 9. So we have to square 4 to get 16 and square 5 to get 25. So what I wanted to show you was consistent patterns don't always have to lie across the outputs. They can connect the inputs and outputs as well. Now, our second skill is to be able to be given an equation and create our own table. So remember, an equation is a way of describing how the relationship always functions. In other words, it's the rule given to us at the beginning. So to create an input-output chart, you would first have to draw your input-output chart itself, like the rows and columns, but then you would substitute each input value one at a time for x to figure out what y is. So for example, if we have y equals negative 3x, we could create this input-output table and substitute means to replace, the input value, which is our x, with the number that we know. So we know that x is 1. So if I put 1 in for x, which is multiplication because they're touching, then y is equal to negative 3 times 1, which is negative 3. Now I can do the same thing for the next input. For this situation, x is 2. So I'll substitute 2 for x, which is multiplication because the negative 3 is touching the x. So y is equal to negative 3 times 2, which is negative 6. Now I can continue to do that for the next inputs. If x is negative 3, if x is 3, then y is negative 3 times 3, or negative 9. If x is 4, then y is negative 3 times 4, which is negative 12. Whoops. If x is 5, then y is negative 3 times 5, which is negative 15. Now, you can check your work to your table by looking to see, what did x constantly change by? Well, do you see how x has a coefficient of negative 3? That means for every x, there's negative 3 times as much. The coefficient of x is your constant rate of change. And if you look here, minus 3, minus 3, minus 3, minus 3. The constant rate of change in your outputs can always be found as x's coefficient if y is all alone on the left. Okay, let's look at some more examples. The first one that we're going to look at is x squared plus 1. So we're going to have to take our input, square it, and add 1 to it. So I'm going to write it here so we don't have to erase all the time. So we'll have negative 2 squared and add 1, and that'll tell us what y is. Well, what's negative 2 squared? What's negative 2 times negative 2? 4, positive, plus 1, which is 5. So our output is 5. So for an input of negative 2, this rule would output 5. Let's do the same thing for x is negative 1. Put negative 1 in for x. We have negative 1 squared plus 1. Well, negative 1 squared means negative 1 times negative 1, which is positive 1, plus 1 more, which is 2. So if I input negative 1, I'll output negative 2. Let's do x is 0. So I have 0 squared plus 1. 0 squared means 0 times 0, which is 0, plus 1 more, which is 1. Now we have x equals 1. So we have 1 squared plus 1. 1 squared is 1 times 1, which is 1, plus 1 more, which is 2. We have x equals 2. So we have 2 squared plus 1. 2 squared is 4, plus 1 is 5. Now, do you see how, and this is not a technical term, but do you see how this input-output table almost reflects itself? Everything to the left is the same as everything to the right. That's the result of squaring. Because remember, when you square something, your answer always comes out positive. Because a positive times a positive is a positive, and so is a negative times a negative as a positive. Alright, let's try the next one, which has absolute value symbols. These are absolute value symbols, which mean how far a number is from 0. Now, we're going to have to take our x and substitute it in, our x value in for x. Notice the 2 and the x are touching, so this will be multiplication when we substitute in. So we have the absolute value of 2 times negative 2 minus 5. Absolute value is a grouping symbol, so we have to do what's inside first. We have the absolute value of negative 4 minus 5. So we still have the absolute value symbol, so how far away from 0 is negative 4? And it's 4 away. And 4 minus 5 makes negative 1. So an input of negative 2 outputs negative 1. Now do the same thing for the next input. Put negative 1 in for x. So we have the absolute value of 2 times negative 1 minus 5. Do what's inside first. 2 times negative 1 is negative 2. So the absolute value of negative 2 minus 5. How far away from 0 is negative 2? 2 minus 5 makes negative 3. Substitute 0 for x. 2 times 0 is 0. How far away from 0 is 0? 0. And 0 minus 5 makes negative 5. Now remember, whenever we input our value for x and we squared it, we said the outcome was always positive. The same is true for absolute value. So watch what's going to happen when I substitute 1 in for x in terms of what happened when we substitute negative 1 in for x. So with the absolute value of 2 times 1 minus 5. 2 times 1 is 2 minus 5. How far away from 0 is 2? 2 minus 5 is negative 3. And last one, absolute value of 2 times negative 2, 2 times 2 minus 5. 2 times 2 is 4. So we have the absolute value of 4 minus 5. How far away from 0 is 4? 4. And 4 minus 5 makes negative 1. Now let's look at some real-world situations and work to fill in their input-output charts. This one says the number of campers, Y, a summer camp will allow to register is always 4 times the number of counselors available. So you can see that for every counselor that we can have 4 campers. So the equation Y equals 4x represents this situation because we're going to be constantly increasing by 4 campers every time we add another staff member. So Y is equal to 4 times x. So if we take x and multiply by 4, we get how many campers that we have. If we have 1 counselor, we can have 4 campers. 4 times x. If we have 2 counselors, we can have 8 campers. If we have 3 campers, we can have 3 counselors, we can have 12 campers. If we have 4 counselors, we can have 16 campers. If we have 5 counselors, we can have 20 campers. And last, if we have 6 counselors, we can have 24 campers.